Hello, in this example, we're going to take a look at when we want to integrate something where we have a rational, but at least one of the factors has a power on it. What do we do in that case? We've seen all of our unique factors where we might have a quadratic, we might have linears, and how we write those factors. But how do we deal with the partial fraction decomposition when one of the factors, or both, or however many there are, have an extra power? And when I laid out the steps that we're going to go through, there was a comment made that said building the powers, that when the powers are repeated, we're going to build them up. Every factor will get a fraction. What that means here is there's actually three factors. There's one of this 3x minus 1, and there's two of these x minus 1s. So when we start our partial fraction decomposition, we want there to be three fractions, one for every factor. The first factor is 3x minus 1. The second factor is x minus 1. The third factor is x minus 1 squared. We're going to build up these powers. If this was a cubed, it would then be plus a fraction of x minus 1 cubed. We'll build up those factors to get as many fractions as we need to get up to that power. Some reasons why we need to do that is that if we didn't build those powers and they had the same powers, then they'd already be fractions with a common denominator, and we would just be able to add those straight across. We don't want them to have a completely common denominator because we're trying to break these down into as small of pieces as possible. So we want to build up those powers. Something to think about as to why we want to build up these powers of 1 over x plus 2 over x squared ultimately will end up being equal to x plus 2 over x squared. Where these are easy to integrate, this one we could take care of if we split it up. So there is some reasonings behind building those powers, but every factor will get a fraction, and we build up the powers from those factors. Now, looking at what these factors actually are, we have linears in all of them. But wait, this one's a square? Does not matter. It's based on a linear factor, so we're just going to put a constant on top of it. Again, writing out that example again. We already have that simplified down. If we put more to it, we could have broken it up in a different way. So all of these are at their base linears. So we're going to put an A, a B, and a C, since we only need constants above a linear. Now we need to go through that process of finding these pieces. So we're going to multiply by this common denominator to clear the fraction. When we multiply by that denominator on the left-hand side, it just clears out the whole denominator. Now, when we take A and multiply it by 3x minus 1 times x minus 1 squared, the 3x minus 1s will cancel. We get A times x minus 1 squared. When we multiply B by both these fractions, we will get B times 3x minus 1 times a single x minus 1. One of the x minus 1s will cancel. We will leave one behind. And then c, when we multiply by our common denominator, since c has both the x minus 1s, we're only multiplying c by 3x minus 1. We can take several approaches here. We can either multiply this all out, or we can use the nice value approach. We're going to have to use a little bit of extra logic at the end, but we're going to take the nice value approach. So first, if x equals 1, when x equals 1, x minus 1 is 0. So this piece would be 0, and this piece would all be 0 because of these x minus 1s. But we'll have left c times 3x minus 1 to give us 1 squared plus 3 times 1 plus 6 is equal to, this whole thing is 0, the second whole piece is 0, the c is all we have left. C times 3 times 1 minus 1. Simplifying that down, 1 squared plus 3 plus 6 is 10, and 3 times 1 minus 1 is 2. So C equals 5. The other 0, or the other nice value that would make things go away, is what would make 3x minus 1 equal 0. 3x minus 1 equals 0, then x will equal 1/3. That is the other value we're going to use. When x equals 1/3, b, when I put 1/3 in here, will go away, and c will go away. Meaning I am left with 1/3 squared plus 3 times 1/3 plus 6, which is going to be equal to a times 1/3 minus 1 squared. Simplifying this down, we get 1/9 plus 1 plus 6, which is equal to 1/3 minus 1 is negative 2/3 squared. Combining like terms, 1 plus 7 is, 1 plus 6 is 7. 7 written as a fraction with a denominator of 9 would be 63/9, meaning we have altogether on this left-hand side 64/9. The right-hand side, we have a, and negative 2/3 squared is 4/9. We can clear that denominator of the 9, or multiply both sides by 9/4. The 9's cancel, and 64 divided by 4 is 16. So a equals 16. We have a and we have c. The problem is there's no nice value as of right now, without a little bit extra work, to pick for b that will make a and c completely go away. Because the nice value that made c go away will also make b go away. And the nice value that made a go away will also make b go away. However, since we only have one value to find, and we have found the other two, we can just pick another nice value. And a particularly nice value to use in almost any situation is 0. X equals 0. We also know c has to be 5, and a has to be 16. So we can use all of those, and all we're left with is b. So if x equals 0, our left-hand side becomes 0 squared plus 3 times 0 plus 6. And our right-hand side becomes A is 16 times 0 minus 1 squared, because x is 0, plus we don't know anything about B, but we do know that x is 0. So plugging 0 in, we have B times 3 times 0 minus 1 times 0 plus 1. And then the last one is C. We know C is 5 and 0 at x is 0. So plus C, which is 5, 3 times 0 should be a minus 1 here. Sorry. Minus 1. So solving this out, zoom out to see everything together. All we've done is plug the values in here. 0 squared is 0, 3 times 0 is 0. That left-hand side is just 6. 16 times 0 minus 1 squared. Negative 1 squared is 1, so we have 16 times 1. Plus B times 3 times 0 minus 1 is negative 1. 0 minus 1 is negative 1. Negative 1 times negative 1 is just 1, so I'm going to erase that out. That this is negative 1 and this is negative 1. So they cancel each other in that multiplication. And then the last part, we have plus 5 times 3 times 0 minus 1 is 5 times negative 1. Giving us the equation 6 plus 11, 6 equals 11 plus B, or B equals negative 5. So we can combine the strategies a little bit of maybe I can use the nice strategy to find many of my values. And then once I have a couple values, I can additionally start plugging other things in to help find anything remaining. But zooming all the way out again, if A equals 16, B equals negative 5, and C equals positive 5, we have our partial fraction decomposition. So to find this integral, the integral of x squared plus 3x plus 6 all over 3x minus 1, x minus 1 squared is equal to the integral of our partial fraction decomposition. And each one of these, easy to integrate. You may want a u sub to really fully see them, but each of the u subs would be their linear factors. And this integrates into 16/3, the natural log of 3x minus 1, minus 5 times the natural log of x minus 1. And then be very careful with this last one. It's not a natural log anymore. Remember that the integral of 1 over x squared is equal to the integral of x to the negative 2, which add 1 to the exponent is negative x to the negative 1 or -1/x. We have this form on the last one. So when we integrate it, it will become -5/x - 1 without a square plus c. And there is our integral of x squared plus 3x plus 6 all over 3x - 1 times x - 1 squared.